for regular languages, we first introduced the machine, this DFA or NFA, whatever, and then we showed their equivalence and all those things. Now, for context-free languages, we didn't use any sort of machine or automata to define that class of language, right? So this is what we are going to do now. So this type of automata is called push down automata. So again, we will define this automata, we will define the acceptance condition, okay, and later we will prove some theorem which will show that this class of language, the class of language that is accepted by this push down automata, is exactly the class of context free languages, which we defined earlier in terms of grammar. Okay, so we will show equivalence between this machine and context free grammars. So what is a push down automata? So it is it behaves like a epsilon NFA, but it also has a stack. Okay, so finite, what was the finite in finite automata? The memory was finite, right? So the number of configuration was finite, and the configuration was just the state. Okay, the current state is the current configuration. That was the configuration for finite automata. Okay, so here we are talking about push down automata. So here we will also have states. It will also go through this input symbols and will change state and all those things, but on top of that it will also have a stack, and this stack will somehow enable it to be in potentially infinitely many states. So that is why it's no longer a finite automata. Now, what is a stack? From data structure course you already know what a stack is. It is some kind of data structure where you can put some data. So you have some data, you put something else on top of it, put something else on top of it. We call it push operation. And then you can also retrieve data, and when you are retrieving data, you are kind of deleting the data from the top, right? So this order is important. I mean, when you have this data structure, you cannot just remove this data from the middle, right? So you have to read or remove the data from the top only, and again you can add data only to the top. It's not a random access memory sort of thing. So I'll not waste time on describing what a stack is, because you are supposed to know what a stack is. If you do not know, then you go back to your data structure course and read thoroughly about stacks. But here we do not need our stack is a very theoretical sort of stack, because in our case, what is data? So data is just some symbol or string, right? So here so data is just a string or symbol. So the stack itself is represented just by a string. So what is a string? The symbols that we have already pushed into the stack, all the symbols that are already inside the stack, right? So the stack looks something like this, and you see that we have written it in a horizontal format because it's easier when we are interpreting this as a string instead of a vertical sort of structure. And also we adopt the convention that the top is at the left. Okay, so you can also have the convention that it's written in the reverse order and the top is in the right, but for us it is convenient that we write it in this fashion, from right to left, and this leftmost symbol is the top symbol. So what are the operations on stack? You can either push data from this side, okay, this open end, this top end, or you can retrieve the data from this side. For example, you can remove this X, right? Now in our PDA, this push down automata, we consider only a single operation, and it's a combination of both a pop and a push. So the operation is, you first pop the top symbol, so it has to have at least one symbol. You cannot do this on empty stack. So this operation is you first remove this top symbol, so you remove this X and then replace it by some string. So here we are pushing multiple symbols, right? So it's like a multi push, and the pushing order is, again, since we are writing it from right to left, the pushing order is first Z, then X, then Y. So you see that we first remove this X, okay, you just remove this X from here, and then suppose you are pushing a string YZX. So you are pushing this string YZX means first you are pushing Z, then you are pushing X, and then you are pushing Y. So this is just our convention. Okay, there is no deep thing about this thing. Now this operation is general enough to actually accommodate push or pop separately, but we will all in PDA we will always use this replace operation. So what is happening, we are replacing the top symbol by this thing. Now in general what will happen, so suppose this is in fact the general scenario, right? So you just replace one symbol by multiple symbols. Now if you want to kind of simulate a single push, okay, so you do not want to remove this thing, so you can easily do that by, say, your stack is this. So the bottommost symbol is x1 and then the topmost symbol is xn, and you do not want to remove this thing. So what you can do is you can say that I am replacing this xn by xn plus 1 xn. Okay, so that means you kind of remove this xn and then again put back this xn plus 1 and xn, and in practice you are just putting this xn plus 1. So this xn is still here, right? So similarly the pop operation can be simulated, because see, this is a string and this can also be an empty string, right? So if you replace this top symbol, say xn plus 1, by this empty string, then you are just removing this string and then you are pushing back nothing, right? So in fact you are just removing one symbol. So you can simulate push and pop as a special case of this replace operation. And in fact you can simulate, say, do nothing. How to do that? You just replace the top symbol xn by xn, right? So you first remove this xn and then again put back this xn. So in fact the stack doesn't change, so you are not doing anything to the stack. So this is this substitute operation. Substitute means substituting the top symbol by an arbitrary string. So this is the operation that is going to be used for our automata, this push down automata, right? So let's see what a push down automata is. Now you remember that for finite automata we had a picture like this. So the machine, the idealized machine, looked something like that. That you have a semi-infinite tape. So it has a start, and it is infinite because you can accommodate any string into it. The string itself is finite, but the tape is infinite. So that means it can accommodate any string of any length. So and then this machine has a read head, right? So the read head starts at the initial position, and at each time step the read head moves to the right, okay, through this tape, and at any point of time it is looking into some symbol which is current symbol, and depending on this symbol and its current state, so again it initially it has some state q0, and while it is jumping from this input symbol to another input symbol, the state changes, and what will be the next state, that is determined by the program of this finite automata. So the program you can draw as a transition diagram, or you can write as a transition table. So depending on the current state and the current symbol, you determine the next state. But if we allow non-determinism, it is not just a single state, it can be a set of next states, right? And in that case, I'm on the same current state and some same input symbol, you can switch to multiple next state. So that was finite automata, non-deterministic finite automata. And you can also have epsilon move, where you do not forward this read head. You stay here, so you are not processing the input symbol. You are just changing this state, right? So this was epsilon NFA. So PDA is similar, only the difference is that you will also have a stack, so it will look like this. So this part is same as this epsilon NFA. So it can have this non-deterministic transition, epsilon transition. So depending on this current symbol and the current state, there is something else also, but you have this current symbol, current state, and in the next time step you will have the next state. But in a single time step, in a finite automata, the head just moved from here to here and only the state changed. So these two things will happen here also. The head will move and the state will change, but also it will act on the stack. Okay, so in the middle of the information processing, the stack already has some symbols, and when you are going through one time step, so along with moving the head and changing the state, you will also perform a replace operation here, right? And what was the replace operation? You are just replacing the top symbol by a string, right? By the finite string. So this is the operation you will do in one time step, right? And another crucial thing to notice is that, so here this input symbols are coming from what? Input alphabet, right? This we saw in finite automata, and we use this sigma for that alphabet. Now here in stack also we are manipulating some symbols. So these symbols are coming from a different alphabet. We will use this capital gamma for that alphabet, and we call it stack alphabet. So stack symbols are coming from the stack alphabet. They may be same, there might be some overlap, but there might not be. So sigma and gamma, they can be equal, they can be unequal, they can be overlapping, whatever. The point is they need not be same. Okay, so we are actually talking about two different alphabets. So one alphabet is for input symbols. So this is the alphabet over which your language will be defined, because your strings which you are supposed to either accept or reject, so that will come from this alphabet. And for its internal use, for this stack manipulation and all, so this machine is using this stack alphabet. So this is its internal thing. Okay. So how does a transition look like? So again, I'm just going back to the finite automata case. So the transition diagram here depicted the fact that depending on the current state and the current input symbol, you are just changing the state from here to here, right? So here also you have a current state, say Q, and you are seeing some current input symbol. Okay, so this symbol let's say is A, and so this is the current state, and this A is current input symbol, and this A is coming from this sigma. And also, since we are allowing epsilon transition, this A can also be epsilon, so we will come to that later. For the time being, for simplicity, just assume that this is just symbol in sigma, but this can also be epsilon. Now depending on this Q and A, you made the transition for finite automata, but here it will also depend on the top stack symbol, because you see, depending on this you decide how to replace this string, right? And also depending on this you decide which state to move on in the next time step. So now the transition depends on this current state, current input symbol, and the top stack symbol. So whatever is here, right? So it depends on this state, this symbol, and this top stack symbol. So top symbol we can say, right, or current stack symbol, whatever. And this decides two things. Okay, first of all, it decides what the next state will be, or what the set of next states will be, because we are also allowing this non-deterministic transition. So yeah, it determines about the next state, and also it determines what is the string that will replace this top stack symbol. So this will be replaced, right, in one time step. So depending on this Q, A, and Z, depending on this three things, so this will be decided, and the string that is supposed to replace this this Y in this stack. So the transition function looks like this. It takes a state, it takes a current input symbol, it looks at the top stack symbol, okay, and depending on that it gives you a pair of two things. So what are those two things? The next state and the string that is supposed to replace the top stack symbol. And since we are using allowing non-determinism, this is actually a set of such pairs. Okay, this is a finite set of such pairs. You cannot have infinitely many things here. So just to make it more clear, if you have such a transition, okay, and suppose you have already partially processed your input. So this is your input consisting of input symbols. So this A's are coming from what? This input alphabet sigma, right? So you have the symbols, and even after this here you have some A, K plus 2, K plus 3, whatever. So these are say occupied, and the whole input takes say some place. Up to this, say you have your input, and you are you have already processed this input symbols, and now you are looking at this symbol. This is the current input symbol. Your read head is here, and this is your top stack symbol. Again, while processing this, you have already done something to your stack, so you have some multiple stack symbols in your stack, and this is the top stack symbol, and you have some state as your current state. And now if you have a transition function and which says that this thing is this set, so that means non-deterministically, first of all, it takes one of this thing. So you take some pi gamma I, okay, non-deterministically from this. And what is this gamma I? So this is a string over the stack symbols, okay, so this stack alphabet. So this gamma I, so this gamma I is this small gamma I is a string over this stack alphabet, this capital gamma, okay. So now it non-deterministically chooses one of this thing and then make this transition. So transition means first of all the read head moves, so that means this A is processed, and the next state is this pi according to this. So the state changed from Q to pi, and then this top stack symbol, so this symbols remain same, so from Z1 up to Zm. So this is not changed. This top symbol is replaced, so this Z is replaced by this string. So this is a collection of multiple stack symbol, right? This small gamma I. So the stack is changed in this fashion. So this is just one time step, okay. So in some time step you are here, and in the next time step you are here, and it is non-deterministic because this I is chosen non-deterministically. So this we showed for symbol in sigma, but as we mentioned before, it can also be a epsilon transition. And what is the epsilon transition? That means it is not reading the input symbol, and without reading the input symbol it is making a transition. So epsilon transition will look something like this. So first of all, we have this here. So from this shows that the current state is Q, and this shows that it is not processing any input symbol, so just like this finite automata. And this shows that the current the top stack symbol is Z, and depending on these three things, this Q, epsilon, and in fact here the current symbol is not there, decide to make a epsilon transition. So depending on this Q and Z, you are making this epsilon transition where you are changing the state. Again, the state is changing from Q to Pi, and this top stack symbol Z is being replaced with this small gamma I, right? And here you see the difference is that the head didn't move, so that means it didn't process this input symbol. So the current symbol here is again the current symbol here visible because of this epsilon, right? So you have seen this similar thing in epsilon NFA, so you should pick this up accordingly. Now, so this is just one step of this machine, right? So this was a step for where this A is coming from sigma, and this is the step for the epsilon transition. So one of this thing will happen in one time step, and the machine starts with an initial configuration. So for finite automata, what was the initial configuration? So as I said, in the initial configuration in the finite automata, the head was at the leftmost position. Okay, so none of the symbols are processed yet, so it will start processing it from here, and the head will move from here to the end of the input. And initially the state was Q0. So here also we will have a special state, a start state, Q0, right? A starting state or start state. And as I said, this stack cannot be empty, right? Because the operation is replaced. So if there is nothing to replace, then the operation cannot proceed. So at the very beginning, when you haven't even started with any of this input symbol, your state is Q0, and your stack contains again a special stack symbol. So again this Z0 is coming from this capital gamma, from this stack alphabet. So a special symbol is marked there. So your stack will contain the Z0. So the machine starts with this configuration, the state as Q0 and stack containing this special symbol, start symbol Z0. Okay, this is a starting configuration, and the head is at the leftmost state. And starting from this configuration, it will proceed according to this sort of transition diagram or transition function or transition table, whatever you use. So yeah. So now the behavior is kind of defined. So you know that there is a set of states. There is a input alphabet sigma, there is a stack alphabet gamma, and there is a transition function delta, there is a start state Q, and there is a stack, this start symbol from this stack alphabet, that is Z0. So all these things define our PDA, and it also has a set of final states. So like this finite automata, which is a subset of all the states. So mathematically speaking, so this 7 tuple is a push down automata, and this is a finite set of states. This is input alphabet, this is a stack alphabet, this is the initial state Q0, this is the start symbol, which is a special symbol in gamma, and this is the transition function. So now see the signature of this transition function. Okay, so it takes a state, then this A can be either a symbol in sigma or it can be epsilon. So here the domain is sigma union this epsilon, right? And then this is the top symbol, the top stack symbol. This is not a string of stack symbols, right? So this is just the one stack symbol. So that is why this is just gamma. Okay. And then this maps to what? A finite subset of this thing. A finite subset of pairs. And the first component of the pair is a state, which is the next state. And the second component is a string over stack symbol, which is supposed to replace this top stack symbol, right? But it has to be a finite subset, so you cannot have infinitely many pairs here, right? So we need to explicitly say finite subsets for PDA. For finite automata we didn't have to say this, because this part only was a subset of states, and since we have finitely many states, so this part was automatically finite. But here, since we are considering arbitrary strings here, so even with finite alphabet you can have arbitrarily many strings, so we need to explicitly mention that you cannot have infinitely many pairs here. Okay, so everything else is finite. This queue is finite, this is finite, this is finite, obviously this will be finite, and so on. So the number of state is still finite, like finite automata, but it's no longer finite automata because of the stack, because now the stack can have infinitely many configuration, which is sort of an internal memory for this machine, right? Okay, so like we had this transition diagram for FA, this epsilon and FA or whatever, so we can also draw this sort of transition diagram for PDA. Now this picture is taken from Hopcroft, Motomani, Ullman. Okay, so I generally follow Hopcroft, Ullman, but in Hopcroft, Ullman you won't see this sort of transition diagram for PDA. So this you can see in Hopcroft, Motomani, Ullman. So now see, I mean, it's almost like this epsilon NFA that you have already seen 100 times by now. So it says that you can have a transition from Q0 to Q0 if your current input symbol is 0 and the top stack symbol is Z0, and in that case you replace this Z0 by 0Z0, right? This is what it means, right? So it means and similarly, I mean, you can make a transition from Q0 to Q0 if your current input symbol is 1, top stack symbol is Z0, and in that case you replace this Z0 by 1Z0, right? So here what is the input alphabet? So the input alphabet is this, right? 0 or 1. So this is the sigma, right? And what is the stack alphabet? So the stack alphabet always contains this Z0, and then you see these are the strings that goes into the stack. So this 0Z0, this is a string that will go into the stack. So this 0 is part of stack alphabet, this 1 is part of stack alphabet. So you see that there is a overlap here. So here for sigma we have this 0 and 1, and this gamma we have Z0, we have Z0 and 0 and 1. Okay, so they are not disjoint in this case, but at least different. And you also have epsilon transition. So here you are not processing any input symbol, but you can make only this transition if your top symbol is say Z0, and in that case you replace it by Z0. So still, when you are making this epsilon transition, you have to match this top stack symbol, right? Here the transition is defined for all possibilities of the stack symbols, so it may not be the case, it may be partial and those sort of things. For example, here you can make this epsilon transition only when the top stack symbol is Z0. So if your top stack symbol is not Z0, so then you cannot make epsilon transition. Now like we have this bifurcation diagram in NFA or epsilon NFA, so here also you can easily see what kind of bifurcation it will have. But before that, we need to define something called instantaneous description, because so far we have only defined how the machine proceeds from one configuration to another configuration, and we showed the initial configuration, which is just Q0, Z0 and head at the leftmost position, right? So starting from this initial configuration, it moves from another configuration according to the transition function. Now this configuration that we are using, this informal term, so now we formalize this thing, what we mean by a configuration of the PDA at some time step, okay? While you are processing your input, so your head started from here and it will have to go up to this point, right? In fact, up to this point. So, and in the middle, after some time it has reached something in the middle, so this is the current input symbol. So that means it has already processed this A1 up to AK-1, and it is yet to process this AK1 up to AN. So this is the remaining part of the input, and this A1 up to AN is a whole input, right? So at this point, how do you describe its current configuration? Okay. Now in case of finite automata, the configuration was completely described by the current state. Okay. Here you will also have to say what the stack is. What the symbols in the stack is. That means together this is a string. So this state, this Q and the string, say this Zm up to Z1. So again we are adopting this convention that the string is Zm up to Z1, not Z1 up to Zm. So we are writing it in this way. So anyway, so these two things kind of are required to describe the current configuration of the machine, and on top of that, it is also helpful if we also include the remaining part of the input in the description of our current configuration. So the remaining part here is AK up to AN, right? Because it is yet to process this symbol. So the instantaneous description will have a state, the remaining part of the input, which is a string over sigma, right? So this is input alphabet, that means this is a string over input alphabet. So this is the remaining part of the input, and then the string in the stack, and this string is over this stack alphabet, because these are symbols from this capital gamma, right? So this is a string over this capital gamma star. So these three things are used to describe the current configuration, and we call it instantaneous description of the PDA, ID in short. Okay, so this ID of PDA is some triplet QW gamma, where Q is coming from this capital Q, W is some string in sigma star, and gamma is from this capital gamma star. Now when we formally define this, we just define it as a triplet. Okay, we do not impose the interpretation as part of the definition of ID. So this can be any triplet where this Q is coming from here, W is coming from here, and gamma is coming from here. Any triplet that you can form using this Q, sigma, and gamma. So that is a ID. Now that is a ID which may not be reached by your PDA. It is possible that you never reach some odd combination of this Q, W, and gamma, but that's okay. I mean, any triplet of this form we call this instantaneous description. Now it's a different matter whether we can actually reach that instantaneous description as part of processing our input or not, and this triplet is interpreted as this, what we already discussed. So given this triplet, this will be actually interpreted like a current configuration of some PDA, where this Q is current state, this W, this thing is remaining part of input, and this small gamma is the symbols in the stack in this order. Okay. So now that we have a formal way of describing the current configuration of a PDA, now we have this relation. So we will call this trans-style. So this trans-style relation relates two configurations, that means two IDs, two instantaneous descriptions, I mean, such that from one configuration you can reach the next configuration in one time step. Okay. So after processing your input, suppose you are here, so what is the remaining input? So this A is still remaining, and after that you have this W, which is a string over your input alphabet sigma. So the remaining string is AW, right? So this is AW, and your state is say Q, and what is the stack string? The top symbol is Z, and after that you have multiple symbols. So there is a string over your stack alphabet. So alpha is a string here. So the entire string is Z alpha. So your current ID is this Q, AW, Z alpha, and from here, suppose your transition function is such that if you are in state Q and if you are seeing this current symbol A, so this is your current input symbol A, and your current top stack symbol is Z. So then this is one option. So it's a non-deterministic machine, but this is one option among many options. So your next state will be P, and this Z will be replaced by beta. So what will be the next configuration? First of all, the head will move. So the remaining input is now just W. The state is P, and this Z is replaced by beta. So this becomes beta alpha. So this will be the next ID. So these two IDs will be related by this relation if you have this pair in this delta QAZ. And this we take as a definition of this relation's trans-style. So this is the definition. And you remember that we also allow epsilon transition. So this A may not be just a symbol in sigma. So it can also be epsilon. So in that case, it will be an epsilon transition. Here you will have epsilon, but still it will depend on this Q and Z. And yeah, I mean, so this will be the definition, that this ID is related to this by this relation if you have this pair in here, where this A is either a symbol or epsilon, this W is a string over input alphabet, Z is a stack symbol, so it's just a member of gamma, not gamma star, while this alpha and beta, so they are multiple stack symbols. So that is why they are strings over this capital gamma. Okay, and these are states. PQ are states in this capital Q. Now once you have this single step relation, we can now talk about multiple steps, right? So what we have here is, so first of all, the formal definition of ID is just any triplet here. So again, as I said before, as part of the definition, we do not care whether some triplet can be reached or not. So that will be handled by this relation, by defining this relation. But when we are just defining ID, so ID is any triplet of this form. So it has three components. The first component is a state, the second component is some string over input alphabet, and the third component is some string over this stack alphabet. The interpretation is as I mentioned before. So this is how you are supposed to interpret this thing, but it can be any triplet from here. And how the IDs move from one ID to another ID according to the transition function, so that is captured by this transtyle relation. So as we just mentioned, so this will be the definition of this transtyle relation, right? And then like we had this direct derivation, and we had a superscript I to mean that it happens in exactly I steps, and we had also 0. So the similar thing we can have for this transtyle thing also. So the superscript 0 means you are going from this IDI to IDI. So this I, J, K are IDs. So so you can go from I to I in 0 steps. So this is just a formality, okay. And then how do you define this I transtyle IJ? So this is true if you can reach J from I in I many steps, okay. This is a non-deterministic process, so you can bifurcate, but yeah. And this star means that you can reach from J, reach from I to J in any number of steps. It can be 0, so this can be I, and you can have 0 here. It can be 1, so you can have just this transtyle, or it can be 2, 3, 4, any finite integer. So if it happens, then we say that I transtyle star J. And also like this this derivation kind of relation, if we are talking about say more than one PDA in a single proof, and we need to write down this relationship for both machines, then we use this subscript M to explicitly show that we are talking about the machine M, okay, because this relation is tied to a specific machine. Once you define this machine, then you have this thing and this delta, and also they are specific to this M. So to specifically mention that we are dealing with M, we write this thing. So here is transition, this bifurcation diagram for this machine that we already saw a couple of slides back. And you see that this is these are IDs, right? So this actually tells you that how the configuration changes, and this means that the input is 1111. You see what is this thing? So this part is the part of the input which is not yet processed. This is the remaining part of the input. Now this is where it starts. That is why the current state is Q0, right? And the current stack string is just Z0. So it just contains Z0. That's the starting configuration. And what is this thing? So this is the remaining part of the input, but you haven't started with the input yet, right? So that means this is the input that is given to you. So the input given is just 1111. Okay, so this is the input, and your head is the read head is here. So you haven't even processed the first one, and your current state is Q. Sorry, Q0, and your stack, if you imagine you have a stack here, so your stack now contains just this Z0, whatever. So this is the initial configuration. So this 1111 corresponds to this, that you are supposed to process this. Now you have multiple transitions here. You have epsilon transitions here. So let's say, let's see if you can make a epsilon transition. So now the current stack symbol is Z0, right? So if we are making epsilon transition, then the epsilon transition should be this, right? Because this should match the current stack symbol. So we are making epsilon transition. That means we are not processing any input symbol, and we are replacing Z0 by Z0. That means we are doing nothing to the Z0, right? But we are changing the state. From Q0 we move to this Q1. So this is one possibility of moving from one ID to another, and this is shown here, right? See, the remaining part, the remaining input is still 1 1 1 1 because we haven't processed anything, because there is a epsilon transition. The state has changed to Q0, and this Z0 is replaced by Z0. That means this is not replaced, and this is not changed at all. On the other hand, if we are taking this transition, so we have to match this thing. So the current input symbol is 1. So yeah, it will be either this, but then the current stack symbol is Z0. So 1 and Z0 we have to match. So this is the 1 and Z0, right? And this says that the stack will be replaced by 1 Z0, right? So this Z0 will be replaced by 1 Z0. That means what? Actually it will just push a 1 here. It will just push a 1 here, right? And then this head will move to this place, right? Because it has already processed this thing. So this is done. So the remaining part of the input is now just this 1 1 1, and the state will remain Q0. So the next ID will be what? Q0, because it has moved to Q0. The remaining part of the input is 1 1 1. So this part is 1 1 1, and the stack is what? 1 Z0. So this is the 1 Z0. So I'll not describe each and every ID here and explain that. You just stop the video here and you yourself go through this bifurcation diagram and match it with this transition diagram, okay, for this PDA, and you should be able to map all this transition to this transitions that I mentioned here. It can be on this input symbols or epsilon transition, but yeah, so I recommend that you stop the video here and just verify that everything just checks out with this diagram, okay. So once you are done with that, we go to the next slide. So this is the initial ID, right? So your head is at the leftmost position, so that means whatever input string is given, the entire input string is remaining, right? So the remaining part is W, which is your given input string, and the start state is Q0, the start stack symbol is Z0, and at each time step the head moves right. So in epsilon transition it stays there, but eventually it will move one by one, and it will process all the input symbols and it will stop here. So everything is processed. So what is remaining? Nothing is remaining. So that means epsilon. So the remaining part of the input is 0 symbols, that is epsilon, right? And at this point you will have some, this will be Q. There's a typo here, so this will be Q. So this is not start state. Again, what is here? So this is some state after multiple steps, after processing all the input symbols. So this will be some state Q. But the point is here remaining part of the input is just epsilon. That means you have exhausted all the input symbols, and then your stack will contain some gamma, okay. So this is where you stop. When you stop, your ID will look something like this. Now at this point you have to decide whether you accept this string or you reject this string, right? So for finite automata it was is fine. If you can reach a final state, you can reach multiple states. So we saw that here also. So you can reach multiple sort of configuration. So you see that it matches, right? So in each of this case, you have exhausted all the input symbols. So here you see you have exhausted all the input symbols. So here you get stuck. You can no longer proceed. So this is a dead end. This is a dead end. But here also you have exhausted all the symbols. Here also you have exhausted all the symbols. And this is a epsilon transition. So you see that here also you have exhausted all the symbols. So you can either stop here, or you can take one more step, or so you can stop here. So you can stop after processing your input. You can stop either here or here or here or here, right? So this part should become empty, and this can be some state, and this can be something, some combination of stack symbols, right? Now when you stop, you have to decide whether you accept the string or not. So as I said, in finite automata it was kind of simple. If any one of this configuration that you reach, if any one of them corresponds to a final state, so then you accept. So here in case of PDA, it is slightly more complicated, because here we actually have two different acceptance criteria. Okay, so either we can accept by final state, or we can accept by empty stack. So I will define them, those two things now. But the point is, you have two different acceptance criteria, and you should not mix this, right? So when you are talking about a PDA accepting a language, or PDA accepting a string, so first you decide which one you should, which one you want to use. You cannot use one criteria for one string and another criteria, criteria for another string. Okay, so first you say that this is my PDA, and then you say that I am going to use this criteria, or I am going to use this criteria. So you choose one of these two things. So before talking about accepting any string or anything, so you take this PDA and you choose one acceptance criteria, and once you have chosen this acceptance criteria, so then you see how we accept this thing or not. So if you have chosen this acceptance by final state, so then what are the strings that you will accept? So if you have chosen this criteria, accepted by final state, so then you look at this. Okay, so this is star, this should be star. Okay, so that means this is multiple step. So this is star, this is star again, and these are all star. So these are multiple step process. This is star. Okay. So yeah, so this is the initial ID, and this is a ID where you have exhausted all the input symbols, because now this has become empty. Now by finals, we accept this by final state, means this state should be one of the final states. So you remember in the definition of PDA, we had this, we also had this F, the subset of Q, the set of final states. So if you are using this acceptance by final state, so then for all strings you decide the acceptance or non-acceptance according to this thing. So whether after you stop with this thing as epsilon, so if this P is some state in this capital F, then you accept, otherwise you reject. Okay. And again, you should remember the non-determinism, right? So this means what? So now this can lead to many final states, final IDs, right? So this says that if this is true for some pair, that means okay, you can reach some other IDs also, but if there is one ID for which this P is a final state, so then you accept this W. Okay. So this is what you do if you are using this acceptance by final state. And similarly, if you are choosing this criteria, so then you have to use this criteria for all your strings. You cannot mix both criteria. So then for all strings you decide whether you accept that string or not according to this criteria. That again you look at the final ID. So that means you have exhausted the strings here. So this epsilon in the middle says that you have exhausted everything. So here you accept if your string becomes your stack becomes empty. Okay. So this is what? This is the stack string, right? So this is the symbols that are in stack. So this says that there is no symbol in your stack. So if you can process your input string, so that after processing all the input string, you can reach an empty stack, then and only then you accept this W. So this is how you accept or reject. So otherwise you reject. And again, this is, so you should remember this non-determinism. Again, you can reach many other final IDs, but if at least one of them is of this form, that is your stack is empty, so then you say that I accept this W by empty stack. So that means when you are saying that my PDA M is accepting something, so you should always mention whether you are accepting by final state or empty state. You should always mention that thing. Okay. And we in fact use two different notation to define these two languages, because this may not be same, right? So this is the set of all strings which you can accept by final state. This is the set of all strings that you can accept by empty stack. And these two languages need not be same. They can be same, but they need not be same, right? So you need to specify which language you are talking about when you are talking about a PDA, and which acceptance criteria you are talking about. So, and for when you are using this acceptance by final state, so in this final ID, this doesn't matter, this gamma doesn't matter. So this can be anything, this can be empty, this can be epsilon, this can be not epsilon. So all it cares about is this P, whether this P belongs to the set of final state or not. And similarly in here, all it cares about is that whether you have an empty stack here or not. Obviously in both cases you have to process all the input symbols, so this should be epsilon and epsilon. But in here it doesn't care about gamma, it only cares about P being in capital F. Here it doesn't care about P, so P can be anything. It only cares about this thing, that this has to be epsilon, right? So yeah, so that means you have two different acceptance criteria, and once you define your PDA and specify your acceptance criteria, then only you can talk about the language accepted by this PDA. And we use these two different notations. L of M is for final state and N of M is for empty stack. And when we are using this, you see that it really doesn't matter what the state of final state is, because we are not using that f anywhere if we are using this criteria for empty stack, right? This can be anything, and we do not need the capital F. We are not using the capital F here if we are using this acceptance criteria. So it is usually the case that if you intend to use your PDA for accepting languages, I'm using this empty stack acceptance criteria. So generally you define your F to be empty. So in this case, generally we define F to be empty, but this is not mandatory, but this is just a convention because we are not using this F in this case. So if you intend to use this acceptance criteria, you generally define your F to be just empty. And this is the thing that you should remember. These two languages are different languages and they may not be same. Okay.